So, in this set of sessions, we're talking about how stars form, how stars evolve for low mass stars and high mass stars, and we're eventually going to talk about dead stars. For this particular session, we're going to focus on the evolution of low mass stars. So, we're talking about stars where the main sequence star is less than around 2 solar masses. Our own sun is considered to be a relatively low mass star. Again, previously we've talked about how a giant molecular cloud will can collapse under gravity, start to form a protostar that's powered by the gravitational collapse. And as that gravitational collapse heats up the core, makes it more dense, eventually we get one of these main sequence stars. So it's again important to remember that for these low mass main sequence stars, the two properties that determine that we have a main sequence star is that we've got gravitational equilibrium, that is the balance between the inward force of gravity and the outward force of pressure, and that we are fusing hydrogen into helium in the core of this star. Again, the overall reaction for this hydrogen fusion is 4 hydrogen nuclei go in, 1 helium nuclei comes out, plus a lot of energy, plus a lot of neutrinos. Now, depending on the exact conditions in the core, we can have different mechanisms, different sets of steps that actually cause this reaction to happen. For low mass stars, we have something called the proton-proton chain. We talked about this a little bit when we talked about the fusion reaction that's going on inside of our sun. Our sun is, again, a low mass main sequence star. This proton-proton chain, I do not expect students to memorize all of the steps of it because it's kind of complicated. But I do want you to know the term proton-proton chain, the way that hydrogen is fused into helium in these low mass stars. Now, the material in the core of this star, so in the core of that star, we have the hydrogen being fused into helium. That material, for most low mass stars, doesn't really mix with the other material in the star. So if we have this star, we have the hydrogen fusing core, and we have this non-fusing hydrogen. We note in some of the outer layers of the star, there is this convection zone that's mixing some material in the outer layers of the star, but the core doesn't really mix up all that much in many of these low mass stars. So even though hydrogen is being converted into helium in the core, the mid and outer layers of the star are still pretty much 3/4 hydrogen, 1/4 helium, and the 2% heavier stuff, the same kind of composition that we've talked about before. However, in the core, that hydrogen is gradually being converted into helium. Well, if this is going on long enough, eventually all of the hydrogen in the core will be fused into helium, and this will mark the end of the main sequence phase. We've said that during this main sequence phase, the core is in a balance where if gravity starts to win and compresses that core, well, the higher density and higher pressure will cause the fusion reaction to run faster, and that will re-support the star against collapse. We talked about this property when we talked about the properties of the sun. But at this point, we have run out of hydrogen in the core of this star, which means we are no longer going to have the kind of balanced star that we talked about when we talked about the properties of our sun. So let's look at what's going to happen next. So the next set of steps is kind of complicated and kind of counterintuitive. So I want to go through this. We're going to see this kind of come up a couple of times. What happens when an ingredient runs out of, what happens when the element that is being fused in the core runs out in the core? What are the steps that are going to happen? So let's say we run out of hydrogen. We run out of core hydrogen. Well, that fusion reaction is going to stop, which means gravity is going to start to win out, and that inert helium core is going to start to collapse. So if we have the mid layers of the star and the core of the star, we have this inert helium core core starts to collapse. Because again, there's no, as it starts to collapse, well, there's no hydrogen left to fuse, so it can't really do anything. But as that inert core is starting to collapse, let me draw this inert core as being a little bit gray so we know it's not going through fusion. Well, as that core collapses, there isn't any hydrogen in the core, but around the core, so if that's the core, then around the core, there is a region that still has hydrogen. It's collapsing along with the core. And what we get is hydrogen. This is looking like a really freaky eyeball. Sorry about that. This hydrogen starts to fuse in a shell around the core. So hydrogen fusion in a shell around the core. Remember, we said that it's only the hydrogen that we've run out of. It's only the core that's run out of hydrogen. Around the core, there's still plenty of hydrogen. So as the core compresses, the core is still inert, but around the core, we get this hydrogen fusing shell. But that hydrogen fusing shell doesn't support the core against further collapse. So what happens here is the core keeps collapsing. The core keeps collapsing. And so does this shell. The shell is collapsing along with the core. The kind of rug's being pulled out from under it. And that shell is going to keep on fusing things faster and faster. So shell fusion increases, but that doesn't support the core against collapse. And we get this runaway shell fusion. So we get this runaway fusion reaction. So again, that shell, it's starting to fuse some of the hydrogen in the shell around the core, but it doesn't have that nice balance we had when the core was undergoing fusion. Because again, the core is still inert, it's still compressing, and the shell is compressing along with it. But that runaway fusion reaction generates so much energy that it actually heats the outer layers of the star and causes them to expand. So what we get is we've got our core. We've got the core. We've got this runaway fusion layer. And the outer layers of this star are just going to massively expand. So the outer layers expand. So the very, very outer layers, they expand so much that those very, very outer layers, their temperature actually goes down a little bit, and we get what's called a red giant. So this whole process forms a red giant star. Again, this process is a little bit complicated, so let's kind of talk through it one more time. The core has run out of material to fuse, so it's going to start to collapse. Around that collapsing core is some material that can fuse, and it's going to start to fuse, but that doesn't support the core. So the core keeps collapsing, and that fusing shell starts going faster and faster, and it produces so much energy that the outer layers of the star get puffed up to many, many times their original size. So on the HR diagram, we have a star like our own sun. When it runs out of material to fuse in the core, when it runs out of hydrogen in the core, it's going to basically move up and to the right on this diagram. massively increasing in size, increasing in luminosity quite a bit, because again, that shell, that runaway fusion reaction in the shell outputs a huge amount of energy, and this causes the outer layers to puff up. Okay. Notice we are no longer fusing hydrogen in the core, we're fusing it in the shell around the core, and we're also not in gravitational equilibrium. The core is compressing. This runaway fusion reaction in a shell around the core that's actually causing the outer layers of the star to massively expand. This is not a star that's in a stable balance. So on the HR diagram, the star moves up and to the right, so lower surface temperature, larger radius, and higher luminosity. And at this stage, the red giant has an inert helium core that's still contracting and heating, surrounded by this hydrogen fusing shell that's just running away with the reaction rate. Now, for comparison, the star Arcturus is a red giant star that's about 1.5 times the mass of the sun. It's already going through this process of expanding its outer layers. It's only 1.5 times the mass of the sun, but it's swollen to 25 times the sun's radius. So this is a scale picture of the sun and the outer part of Arcturus. But the original core, I can't actually draw this original core to be to scale, because this original core is actually smaller than the core of the sun. That runaway fusion in that shell around the core is not very big, and that contracting inner core is really, really small compared to the rest of the inflated size of this star. So again, that in this figure, the relative size of the core and the hydrogen burning shells have been greatly exaggerated just so you can actually see those particular parts. So we've got this red giant, which is puffing up due to this runaway fusion of hydrogen in a shell around that core. But what's going on with the core? Because that fusion in that shell is not supporting against collapse. Well, that core is continuing to contract, and as it contracts, the density increases and the temperature keeps on increasing from a conversion of gravitational energy to thermal energy. So it's causing the core to continue to contract and heat up. And at this point, the core is still primarily supported by degeneracy pressure, but all that's doing is slowing down the process. It's not stopping this collapse from happening. Again, at this point in the core, we don't have any hydrogen left to fuse. We do, however, have helium. So helium, there's a reaction where I can take 3 helium nuclei and convert it into 1 carbon nuclei. Well, let's talk about this process. So helium fusion. Also called the triple alpha process. This is taking in 3 helium nuclei and fusing it into 1 carbon nuclei. Now, this requires a much, much higher temperature and a much, much higher density to occur than helium fusion takes. And let's think about why for a second. Think about this one first. Why doesn't hydrogen go through fusion just at ordinary room temperatures and densities? What is it that's stopping hydrogen from wanting to go through a fusion reaction? Well, think of hydrogen as being those protons. These hydrogen nuclei are just free protons, and they are positively charged, so they don't really want to be near each other. They have an electric repulsion between those protons. So I need that high density and that high temperature to get them close enough together and moving fast enough with enough energy to overcome that electric repulsion and get close enough together that they can actually undergo the fusion reaction. A helium nuclei, each helium nuclei has 2 protons in it, 2 protons and 2 neutrons. So helium nuclei are also positively charged, but since they have more protons in them, they have a greater positive charge, which means they have a greater electric repulsion. So in order to overcome this greater electric repulsion and get this helium to go through fusion, we need much higher temperatures and pressures to make that work. Making things even worse, fusing two helium nuclei together doesn't really work. When you fuse those together, it makes an unstable nuclei that very, very quickly breaks apart. You really need all three helium nuclei to basically run into each other at pretty much the same time to make one carbon nucleus. And this is why this is called the triple alpha process. An alpha particle is a nuclear physics name for a helium nuclei. So alpha basically means helium nuclei. So triple alpha process, three helium nuclei process, converting three helium nuclei into carbon. We'll do three helium nuclei turn into one carbon atom plus a lot of energy. This event, when helium nuclei finally start fusing into carbon in the core of the star, is a very, very violent process. The thing that was supporting the star against collapse was this degeneracy pressure, this thing that we've talked about a couple of times where the electrons don't want to be in the same quantum state, and that actually supports the core against collapse. Well, that degeneracy pressure, it's kind of like a loan. You can get away with using it to support the star against collapse for a little bit, but before the core will re-expand, you have to pay off that debt. So we get this situation called the helium flash. Let's talk about this for a moment. The helium that starts to go through fusion, it starts generating energy when it finally reaches the condition where the temperatures and densities are high enough that helium fusion can occur. But when that starts, since the degeneracy pressure was supporting the core against collapse, the core won't expand. So we get this effect where helium fusion starts in the star, but the core doesn't expand. So that fusion reaction is going to increase the temperature. That increased temperature is going to make the fusion reaction run faster. That increased fusion reaction is going to raise the temperature even faster, increasing the fusion reaction. And we get this runaway helium flash where the core temperature and this fusion rate massively rise very, very rapidly. So the helium fusion can't expand the core at first. And we get this runaway, more fusion, more temperature, more fusion effect. So more fusion, higher temp, and then back to more fusion. So again, this fusion rate skyrockets until finally the thermal pressure can take over and that degeneracy pressure isn't supporting the star anymore. And then finally the core will expand and cool. This extremely rapid output of energy finally reins in that other runaway reaction that was going on in the shell around the core. So this huge energy output expands the fusing shell, and moderates its reaction rate. Well, that reaction rate, that runaway reaction rate in that shell of that shell around the core that was fusing hydrogen, that was what was supporting the outer layers of the star, this massively puffed up outer layers. So kind of counterintuitively, what this does, the overall luminosity of the star actually decreases and the size of the star decreases as well. The energy that it gets produced in the core by this very rapid helium fusion, that basically goes to expand that fusing shell and rein in that other runaway reaction, and overall the size of the star decreases. Again, we can tell this by a couple of different ways. We can use computer models to simulate what happens in the cores of these stars. So computer models predict that a red giant should shrink and become a little bit less luminous after the helium fusion begins in the core. And we can look at star clusters and identify, well, which of these main sequence stars have turned into red giants, and just before that helium flash, what properties do those stars have? And then just after that helium flash, what properties do those stars have? So again, we can use those star clusters and this HR-like diagram. Again, this isn't for all stars. This is for a specific star cluster. We can use that information to find a ridiculous amount of information about the life cycles of stars. So after this helium flash, so afterwards, we've got helium fusion in the core, hydrogen fusion in a shell around that, and that will temporarily be stable again. So afterwards, we have helium fusing core and a hydrogen fusing shell. And this is temporarily stable. Because now we're back in the situation where if that core starts to collapse, well, the helium fusion will start to increase and reassert dominance. If that core starts to undergo fusion too quickly, then the core expands a little bit, lower density, reins in that fusion reaction in the core. And again, this is temporarily stable. And this is kind of going to be what happens as a general pattern for when a star runs out of, or when a star runs out of some kind of fusing material. Let's go through this process. The first part is the same thing that we talked about before. The core runs out of some type of fuel, and that core is going to start to shrink. Around that core, whatever material we ran out of in the core, that material is going to start fusing in a shell around the core. But again, that's not supporting the core, so that core is going to continue to collapse. That shell is going to collapse along with it, continue to heat up, and continue to fuse faster. And that runaway fusion rate will expand the outer layers of the star. So we talked about how when the star runs out of hydrogen, at the beginning of the red giant phase, it goes through these steps. The inert helium core starts to collapse, hydrogen fusion begins in a shell around the core, and that runaway reaction puffs up the outer layers of the star. When the core reaches the temperature where the next kind of material can start to fuse, well, let's talk about what happened during this helium flash. We have these large outer layers of this star, and we had the hydrogen fusing shell, and now we're starting to fuse helium inside of here. So let me fill this in. So we've got the shell fusion, and a new element is fusing in the core. new material fusing in core. So that core fusion, this core fusion reins in the shell fusion. So it reins in that shell fusion. So the energy from the fusion of Y in the core expands the shell that is fusing X, reining in that runaway fusion of X. And since it was that shell fusion that was puffing up the outer layers, well, that's going to cause those outer layers to calm back down a little bit. So the core is now undergoing fusion. That shell has been reined in a little bit. It's not doing as much. And the outer layers are going to settle down somewhat. So without the shell fusion, with less shell fusion, outer layers partially relax back down. Again, this is a complicated set of steps. You probably want to make like a, ordered list of what are each of these steps and how does it go through this, because we are going to be seeing this happen a couple more times. Because at this point, we've got a star that is fusing helium into carbon in its core. And in a shell around that core, it's fusing hydrogen into helium. And again, it's temporarily stable. But eventually, what's going to happen to the helium reaction inside of the core? If it's fusing helium into carbon, what's eventually going to happen to all the helium in that core? Well, eventually, you're going to run out of helium. So again, at this stage, we have this helium fusing core, we've got hydrogen fusing shell, and that's all in the center of this star that's really, really puffed up. But eventually, all the helium in that core is fused into carbon. Well, now we're back to this sort of a situation where, well, now I have this inert carbon core, and that's going to start to shrink. We go through the same things that happen when we ran out of the core hydrogen. A similar set of steps are going to occur when we run out of core helium. This inert carbon core is going to shrink. Helium fusion starts in a shell around the core, inside of a hydrogen fusing shell. And this is not going to support the core against collapse. So this is going to cause a runaway reaction in those shells, and that's going to re-puff up the outer layers of that shell. The outer layers of that star. So this would be our double shell fusion stage. So this double shell burning red giant never really becomes stable. For low mass stars do not generally have enough energy or do not reach high enough core temperatures and densities in order to fuse carbon. So we're just basically left with this kind of a scenario where we've got an inert carbon core, a helium fusing shell around that core, and then a hydrogen fusing shell around that one. And those runaway shell fusions are going to cause the outer layers to keep on kind of expanding. And we get this weird pattern where the outer layers just kind of keep on pulsing outwards with increasingly strong stellar winds. For our sun, when it becomes a red giant, it may actually it's definitely going to envelop the orbits of Mercury and Venus. It might actually reach the Earth and envelop the Earth during these different peaks of the red giant. But at that point, that inert carbon core, low mass stars never reach a high enough temperature or density to actually fuse carbon. When we talk about high mass stars, this is going to change. So we're left with this inert carbon core that's once again being supported by this electron degeneracy pressure against gravity. And the outer layers of the star just keep on puffing up. Those outer layers of the star puff up to the point where the outer layers of the star eventually get ejected. So after this double shell fusing stage, we get what's called a planetary nebula. Actually, before we talk about this, let me go back one slide. In terms of the amount of time that the star is going to last as a red giant, notice that for our sun, this is the prediction for our sun, it's going to last around 10 to 12 billion years as a main sequence star, but then only last a couple 100 million years as a red giant. And these last steps, these would only be like a couple million years during this last kind of final phase of the sun's lifetime. So after going through these transitions as a red giant, those outer layers of the star that were kept on getting puffed out and out, eventually those are going to be just ejected from the star entirely. We get what are called planetary nebulas. So let me zoom in on these pictures. These are mostly Hubble images of some of these planetary nebulas. And what we get is the outer layers of the star have been gradually ejected away. And that leaves this very hot but inert carbon core, basically the leftover core of this star right at the middle of these planetary nebulas. So these are the ejected outer layers of these former red giants and the now exposed core right at the center. These ejected materials, these thin gases that have been ejected away from this star, well, they're still getting a lot of light, and especially a lot of UV light from that now exposed core. That exposed core is still very, very hot at this point. And the ultraviolet light that is ejecting that material, or sorry, the ultraviolet light that is hitting those outer layers, it excites those gases, and we get an emission nebula. We get that emission effect on now these gases are going to be glowing in colors that correspond to what are the particular elements that are in those exposed gases. So again, these expelled gases glow because they're excited by the ultraviolet light from that hot exposed core, which is now what's going to be called a white dwarf. This is an example of one. This is the Dumbbell Nebula. This is an 8-hour exposure. So it took 8 hours for, was this the Hubble Nebula? Hubble telescope taking this? It might have been a different telescope, but this was an 8-hour composite through a hydrogen alpha filter. So this is specifically looking at the emission lines due to hydrogen. And this nebula is about 1,200 light years away. So let me pause that. Sorry about that. Clicked on a link when it wasn't supposed to. That thing at the very center of there, that is the central white dwarf star, basically the exposed core of the star that was here before. And the outer layers of that star have gradually been blown away. We're going to consider this to be a rather gentle blowing away of the outer layers of this star. This will be different from when we look at the supernova events that mark the end of the lifetimes of high mass stars. But the planetary nebula ejects away these outer layers of the star, and those gases are glowing because that exposed star core is giving off lots of UV light, exciting those gases and causing them to glow as emission nebulas. So let's think of some quick discussion questions. If most stars are low mass stars, and low mass stars eject these planetary nebulas at the end of their lives, why don't we see very many planetary nebulas? So try pausing the video and think, as the star has expelled its outer layers, they're now ejected from the star, they're glowing due to the core. Why don't we see very many of these? So pause the video and have a think about that. Okay. Well, let's think about this in terms of how long these things are going to stick around for. We said that the outer layers of the star have now been ejected, so they're moving away and not coming back to the star. They're gradually going to dissipate. And at the same time, that exposed star core, it's doing so very, very slowly, but it is gradually starting to cool off, starting to be at least not those ridiculously high temperatures and starting to just leave behind this white dwarf. So after these gases are ejected away, they are on their way out. These planetary nebulas just don't last very long. They might last only, maybe a couple thousand years before they fade out to the point where we can't directly detect them anymore or easily detect them anymore. And if they don't last for a very long time, well, we're not going to see very many of them. It's only the most recent stars that have gone through this process that we will actually see planetary nebulas for. On the other hand, we said about 10% of stars are white dwarfs. When we looked at the HR diagram, we said around 10% of stars are white dwarfs. Well, why do we see so many? And just as an example, this is the Hubble Space Telescope image identifying a lot of different white dwarfs in this very old globular cluster. So why do we see a lot of those? Pause the video and think about that one. Okay, well, these white dwarfs, we said they're extremely hot and dense, and they are cooling down, but they take a ridiculously long time to cool down. The typical cooling times for a white dwarf would be significantly longer than the current age of the universe, probably estimated to be around 100 billion years, when our universe has only been around for approximately 13.8 billion years. So we actually don't expect to find any what would be called black dwarfs, white dwarfs that have actually cooled down to the point where they're not really giving off much visible light anymore. We don't expect to see them because the universe just hasn't been around that long. So to kind of compare and contrast, these planetary nebula fade away pretty quickly. So we don't see that many of them because you'd have to be watching at just the right time in order to see these planetary nebulas. These white dwarfs stick around for an extremely long time, so we see many more of those. So just to kind of summarize for this HR diagram and the evolution of low mass stars in the HR diagram, we had this main sequence band on the HR diagram, stars that are in gravitational equilibrium and fusing hydrogen into helium inside of their cores. Well, eventually that core runs out of hydrogen, and we have this inert helium core surrounded by a hydrogen fusing shell. This is going to be one of those shell fusion cases that cause the outer layers of the star to expand upwards, and it's going to become a red giant. Eventually, that core that's still being compressed by gravity, that's still getting denser and hotter, that's eventually going to reach a temperature where the star is able to fuse helium in its core. It goes through that helium flash, which rains in that hydrogen fusing shell, causing the star to relax back down a little bit, at least temporarily. But eventually, we run out of helium in the core. So we have this inert carbon core, helium fusing shell, hydrogen fusing shell around that, and that runaway shell fusion is again going to cause the star to puff outwards. And eventually it puffs out the outer layers to such a degree that those outer layers eventually just kind of escape the star, leave the star, and eventually this thing migrates over here and becomes a white dwarf and then would gradually fade out over, again, a very, very long time. So again, that's kind of the trajectory that these stars seem to take on the HR diagram. And we can test and check this by using things like computer simulations and observationally looking at clusters of stars and seeing the patterns on the HR diagram that these clusters of stars at different age seem to follow. So one last example of this. Let's say I've got a binary star system, and let's look at the the Sirius A and Sirius B system. Sirius A is a 2 solar mass main sequence star. Sirius B is a 1 solar mass white dwarf. What I want you to think about, so in a second, pause the video and think about this. When Sirius A and Sirius B were both main sequence stars, back before Sirius B had become a white dwarf, what can I probably say about how their masses compared with each other when they were both main sequence stars? Think Sirius B is further along its evolution. It's gone through more of these steps. It's further along its life cycle. So when they were both main sequence stars, what would I have to have been able to say about their masses? So pause the video and think about that one for a second. Well, let's think about it like this. When we go back to the HR diagram, which main sequence stars went through their life cycles faster? The high mass main sequence stars or the low mass main sequence stars? Yeah, hopefully you remember that the high mass main sequence stars go through their life cycles much more rapidly. Well, if Sirius B is already a white dwarf, it must have gone through its life cycle more rapidly. So when it was still a main sequence star, it must have been greater in mass than Sirius A. In fact, when we actually look at the calculations for this, it's estimated that Sirius B was around a 5 solar mass main sequence star that went through this transformation to a red giant and then planetary nebula and then a white dwarf around 125 million years ago. You might ask, well, if Sirius B was a 5 solar mass star and now it's only a 1 solar mass white dwarf, well, what happened to all the rest of the mass? Well, all the rest of the mass would have been ejected during this planetary nebula phase. Again, the core is still the minority of the star, the minority of the mass of the star. So this planetary nebula for Sirius B, around 4 solar masses of material was ejected away from this thing during that planetary nebula phase, leaving behind this 1 solar mass white dwarf. So that's kind of the overview of the evolution of low mass stars. We talked about how, let me pause this and go back to the original slide for comparison. There you go. So we said for low mass main sequence stars, we've got a low mass main sequence star that's powered by that hydrogen fusion via the proton-proton chain at its core. Eventually that core runs out of hydrogen and moves on to the red giant phase. We have this case where sometimes the core is contracting when it runs out of material, and we get fusion in the shell around that core to puff up the outer layers. Eventually, the core can fuse helium that resupports the star for a bit, but eventually we run out of helium as well. Eventually, as the star runs out of materials to fuse, the outer layers of the star are puffed up and ejected away as a planetary nebula, and eventually leave behind this white dwarf. So that's kind of the overall picture of the evolution of low mass stars. In the next session, we'll talk about high mass stars and the differences in the processes that are going on for those, and eventually talk about the different kinds of dead stars in more detail.